Hey guys, today we're going to take a look at the intersection of two planes. Now there are three possibilities here. Number one is it can look like this, and this is where they are intersecting. Okay, intersecting. Now you will notice that when they intersect as a line because of course they're planes. Now this is just a cross section here of what it would look like. Okay, so it's not actually a point. In 3 dimensions, it would be a line. Okay, the next possibility is that they are coincident. Coincident. Okay, and this just means that basically they're the same plane, right? And so one lies on top of the other. And of course, this makes it look like we've got a big one and a little one, but of course, they would go off forever in all directions because it's, it's just impossible to actually illustrate that. But so, that's basically it, is that the two planes are essentially equivalent, okay? And the final possibility is that they are distinct. Okay. So, let's see. So first of all, how to find the intersection of two planes. What we're going to do is we're going to work with the Cartesian equations, okay? To find points of intersections, what we're going to do is we are going to solve the system of equations. Okay, solve the system of equations formed by their Cartesian equations. So a couple things to note here. Okay, first of all, the normal vectors are going to be A1, I'm going to zoom in here, A1, B1, C1, okay, and A2, B2, C2. Okay. So those are our normal vectors. If the planes are parallel, the coefficients A, B, and C are proportional. Okay, whoops. Proportional. Okay. If the planes are coincident, then A, B, C, and D are all proportional. Which makes sense, because it means they're essentially the same plane. Same equation, same equation. They're just maybe multiples of each other, okay? But of course, multiplying a plane doesn't actually do anything because they go on forever, okay, in all directions. A system of equations is what we call compatible. Compatible. If there is at least one solution, okay? A system of equations is, not surprisingly, then called incompatible if there is no solution, okay? And I won't lie to you, that's not vocabulary that's used ultra commonly, but it is the correct vocabulary. So let's take a look at the first certainly the most interesting of the possibilities when they are not parallel, okay? And so this is where they're going to intersect in a line. So first of all, A, B, and C are not proportional. Not proportional. Okay. And then the normal vectors, N1 and N2, do not give you 0, so they're not. So they're not parallel. Okay, they're not parallel. So if you were to take the cross product, you would not get the 0 vector. Okay. So if you want to quickly check and find out, that is an easy way to do it. Okay. By solving the system, which we'll call star. I don't think I wrote it out as star this time, but you get the idea. What you'll get is you'll get two variables. Oops. In terms of the third. In terms of the third. Okay. Let's see. There are then an infinite number of solutions. Because, of course, the solution is a line, so there's an infinite number of possibilities, because lines go on forever, and we can have any value within the line. And thus, there are an infinite number infinite number of points of intersection, because the entire line is made up of points of intersection. So the intersection is a line. And if we were to try to get the direction vector of this line, what we would do is we'd just take the normal vectors and we would take the cross product. There we go. Okay. So, find the points of intersection of the following two planes. So what we're going to do here is we're going to start out just by writing out the Cartesian equations of these lines, which is what's given to us. But I'll just write them out underneath each other so it's written as a system of equations. So we'll have 3y plus z plus 6 equals 0. Okay, and our second equation, which is then 3x minus y plus 2z minus 2 equals 0. Okay. So what we're going to do is you're going to start by isolating a variable. So in this case, I'm going to isolate z. And if you didn't isolate z, if you isolated a different variable, it would still work. You get a different answer, but it would be the same answer. So like you'd end up with, because we know this one's going to intersect as a line, you'd get the same line, but you get a different equation for that same line. Okay. So if you do one of these and you don't get exactly the same answer as the answers in the book, potentially this is what it could be. Okay, so anyway, so we'll isolate z, and I'll do it with equation 1, and what I get is z equals 2x minus 3y minus 6. Okay, and so then what we'll do is we'll sub this new equation 1 into 2. Okay, so we get 3x minus y plus 2 times 2x minus 3y minus 6 minus 2 equals 0. And if we expand and collect like terms and such, what we will get is 7x minus 7y minus 14 equals 0. So there we go. Okay? So what we're going to do now, because we now have an equation with two variables, so what we can do is we're actually just going to say, well, let's let x equal t. And again, you wouldn't have to pick x to equal t. It's going to make the most sense in this context, although it would have made just as much sense to let y equal t. But anyway, I usually let x equal t. And so what we'll see is if we took that equation we just made there, we got y equals x minus 2, which means that y now equals t minus 2. Okay? And so if we go back to equation 1, where we had z isolated, what we can do is we can replace the x with a t, and we can replace the y with a t minus 2 because of that right there. Okay? Hold on. So anyway, there it is, minus 6. Okay? And so if I expand that, collect like terms, I get that z equals negative t. So what I have now is I have all three variables in terms of t. So the line that is the point of intersection, so the intersection of plane 1 and plane 2, is going to be x equals t, y equals t minus 2, and z equals negative t. And that's it. Now that is the parametric equation. You could come up with the other versions of the equation, but there's no reason to. It doesn't tell you you have to. And so I would just leave that as your final answer. Okay? So there we go. So let's flip over and let's take a look at case 2. So this is where we have parallel planes that are also coincident planes. So in other words, this is the one where they're kind of on top of each other. They're essentially the same plane. We're just writing it out twice. So anyway, remember in this case that A, B, C, and D will be proportional. Okay? Let's see. The normal vectors in this case will be parallel. Okay, which means that if I were to take the cross product, it would equal the 0 vector. Okay. Let's see. One equation in the system is a multiple of the other equation and does not contain additional information. So in other words, the equations are equivalent. Equivalent? I don't know if that's spelled right, but it's close enough. It's probably right. Anyway, so by solving the system equation, what you will get is a true statement. Okay, a true statement, which we talked about in the last lesson. What I mean by that is we will get something along the lines of 0 equals 0, which of course 0 does equal 0. That is true. Okay, so that's what we mean. Okay, and it usually is 0 equals 0, but it doesn't matter. Okay, there are an infinite number of solutions, and therefore an infinite number of points of intersection. Of course, this time, not only is it a line, but it's an entire plane that they intersect in. So, yeah, it's going to be, obviously, it goes on forever. So, and the intersection itself is a plane. Okay, so there we go. So let's take a look at how we would solve one of these. So we're going to find the points of intersection of the following two planes. So there they are. Again, I'm just going to zoom right in. And this one's actually a little easier, although it's more or less the same. It starts the same because you don't necessarily know that this is what's going to happen. Sometimes you will look at it and recognize right away that this is going to be the case, but whoops, nope, not a y, that's a z. Z plus 1 equals 0. Okay, equation 2. We've got -3 plus 6 y. Oops, I missed an x. I'm getting sloppier. 9z, if that's possible, -3 equals 0. So there we go. So there's our two equations. So this time I'm going to isolate the x. Okay. And I generally isolate whatever's going to be the easiest, but it doesn't make a difference. And so what I get is that x is equal to 2y minus 3z minus 1. Okay? So what I'm going to do now is I'm going to sub this new equation 1 into equation 2. So what I'll get is -3 times 2y minus 3z minus 1 plus 6y minus 9z minus 3 is equal to 0. Okay? And if we simplify all of this, I'm going to gloss over the details, but if we simplify through this, it actually equals 0, which means that we get 0 equals 0, which is absolutely true. 0 does equal 0. Okay? So at this point, what we can say is we can say, therefore, the intersection, or how, let's see, so therefore, we'll say the plane, because they intersect as a plane, so we'll say pi is equal to, and it's the intersection of plane 1 and plane 2, which is just x equals 2y minus 3z minus 1. And you could actually use any of these versions because they're all the same, and it would all be true. I could have written out this or this, whatever, it doesn't matter. But generally you're going to write this one here where you isolated a variable. And I'm not sure why that is, if I'm being completely honest. But it is worth noting that if I were to take this equation and multiply it by -3, it would give me that equation. Okay, and so that's why, that's how you can tell. But anyway, the last one here is that they are parallel, but this time they are distinct. Okay? So the coefficients, A, B, and C, are proportional. No? Okay. But A, B, C, and D, so you'll notice we're including D here this time, are not. Okay? Oh, hold on a second. My phone's ringing. Okay. So, anyway, by solving the system, I lost my... what we'll get is a false statement this time. A false statement. And so it will be something like 1 equals 0, which 1 does not equal 0. Let's see. So there is no solution, and therefore no points of intersection between the two planes. Okay? So let's fire through this. I'm going to do this one pretty quickly. So let's see. So we're going to start by just writing out the system of equations here. So we get x minus y minus 2z plus 1 equals 0. And then the other one is minus 4x plus 4y plus 8z minus 3 equals 0. Okay, and so we're going to isolate, and this time I'm going to isolate y. Okay, so I'm using equation number 1 here, which I didn't number them, but there we go. Okay, equation number 1 here, and I'll get y equals x minus 2z plus 1. Okay, and so I'm going to sub 1 into 2. And so I will get, let's see, I get negative 4x plus 4 times x minus 2z plus 1 and plus 8z minus 3 equals 0. Obviously I'm out of room, so I'm going to jump up here. Okay. And we're going to simplify that, and we get, well, if I just simplify that through, actually, that's going to give me 1, I think. Is it 1? Yep. So what it gives me is 1 equals 0, which is false. Okay. So from there, obviously, that's basically it. I mean, you know at that point, once you get that, you can say that there is no point of intersection. So therefore, pi 1 and pi 2 do not intersect. And that's it. Okay? So I want you to try these last 3 by yourselves, and we will take them up in class. So until next time, go Sabres.